there's another kind of reflection that Fresnel's equations can tell us about, and that is an internal reflection. Let's see. So internal reflection means that rather than going from air to glass, from a low index to a high index, you just do the opposite. You go from glass, or some dielectric, say n equals 1.5, to air, n equals 1. Or any case where you're going from a higher index medium to a lower index medium. This is all the same. K incident comes in, K reflection goes out, angle of incidence equals the angle of reflection. And the only difference is when you transmit the transmitted beam, rather than falling towards the normal, it runs away from the normal at a higher angle. And if you think about how we derived that, it's not surprising because the index change is the opposite. So there's theta t. So that's basically the difference. We don't really have to calculate much because in this case Fresnel's equations are the same. Well, it depends on how you wrote them. We could have done Fresnel's equations really for having n1 and n2, and they'd be a little bit more general. We just always assumed this one was 1 and this was higher than 1. We always were kind of doing air to glass. If you do n1 and n2, then instead of just seeing n's in the equation, you see n1s and n2s everywhere. However, we can fix ours to be an internal reflection. You just flip it over. You just say, instead of n equals 1.5, you say n equals 1 over 1.5. So it equals 0.667, say. So if you just plug in 0.667 into our RTE and RTM, that's the right answer. All right. So let's look and see what it looks like. So here it is. This is, let's see, this is RTE. And let's write it out again. Cosine theta I minus the square root of n squared minus or plus minus sine squared theta I over cosine theta I plus the blah, 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 yeah, cosine theta I plus the square root of n squared minus sine squared theta I. So we plot that and plot a similar thing for Tm, and we get this plot. And you say, let's see, well, they start at 0.2 at normal incidence. That's about the same as an external reflection. It would come to about 4% when you square it to get big R. And then they diverge from each other and go towards 1, but then something unusual happens here around 40 degrees. By 40 degrees, they've already made it to 1, and then they stay 1 for higher angles of incidence. So that seems like a really strange behavior to just get out of that. How can this be a constant for angle when it looks like that? That seems a little strange. Clearly, something is going wrong. So let's see if we can figure it out. And here's the deal. If n is less than 1, RTE and RTM, for that matter, can be complex. So if we look here, this is less than 1, and for large angles, like out here, sine theta can get to be up to 1, right? So at 85 degrees, sine theta is 0.9 something. So 0.9 something squared, and if this is 0.667 squared, you can see we have the square root of something negative. So suddenly, we have an imaginary number here. We have real parts and imaginary parts. Real parts and imaginary parts, RTE and RTM, become complex. So if it's less than 1, these are complex, and the condition is pretty easy to figure out. It's if sine theta is less than n. Then this will go, I'm sorry, greater than n, then this will go complex. Okay? It's squared here, but this is also squared. So you take the square root of both, and if this is bigger than this because of the negative sign, it turns R's complex. So here, at low angles where they're real, everything acts normal. They act just like they did before. They're just doing it a little faster with angle. But here, as soon as it becomes complex, we get this strange result that it's claiming that big R would be a constant 1. So for air glass, that's about 42 degrees. Or I should say glass air, actually. So theta, it's called the critical angle. It's where this critical thing happens. It's about 42 degrees. So let's look in detail at what's happening to the plane waves and see if we can figure out why this happens.